Okay, so for doing the rest of the PhD questions, first looking at F. So basically, um, F is actually just a simple, just like halo or the halide addition to this. And whenever you have a hydrogen and a halogen, what's going to happen is that it's going to break the double bond and it's going to just kind of give away the Br to the more substituted and the H to the less substituted, which gives you this answer, of course. However, something to note of is that the solvent here, CHCl, H2Cl2, is usually associated with the addition of like dihalogens, like Br2, for example. And if it were Br2 plus the CH2CHCl, then what the answer would be here would be the addition of two bromines to this double bond. So it would look like that. And this would be specified as being anti because these two are always, the combination of these two is going to produce anti bromine groups on the where the alkene was. However, this isn't relevant because what we have here is a hydrogen with a bromide, hydrobromic acid. So it's just the addition of one bromine to the molecule, which gives us the answer here. Okay, and for 2, we went over that. Take a look at that. And so for H, what you have to look at here is the fact that we have a halogen Cl2, and in this case the solvent is just water, so we're not going to have the CHCl, the H2Cl thing we add 2CH, whatever. But instead, we're going to look at that we're adding an OH group, and this OH group, of course, comes from the water molecule. And the kind of chemistry behind this is kind of like simple, really. You're just going to, the H2O is going to break into H, into OH throughout the intermediate process. And so the OH is going to end up on the more substituted carbon, and the Cl, of course, is up on the less substituted carbon. So it's really just a simple addition of halogens to the molecule, and for that, of course, you need an alkene, and you're just going to add an alkene there. You just need one double bond, one alkene, because this is going to produce essentially just the two bonds that you need from here when you break this double bond. Okay, and now for G, whenever you see PD over C or PD plus like H2, that's usually going to indicate like uh, halogenation using like Lindler's reagent, whatever it's called. What's it called? I don't remember exactly. Catalytic hydrogenation of the alkene. And basically, all you need to know for this is that you're going to break this double bond and you're going to add two alkenes, one here, one here. And these are going to be in syn formation. So they have to be cis, essentially. So to make sure you specify that they're in equal positions, that they're not anti. One thing to know is that if Lindlar's catalyst is ever poisoned with something that isn't C, like with some like acid or something, then what you're gonna have is that if this is an alkyne, this is only gonna break once. So you're gonna have a double bond with your D, and it's gonna break once instead of like breaking again. So that's not gonna happen. That only really applies to alkynes. And so for H, this is a little bit tricky, but we have an SN2 reaction because it's ethyl bromine and because it's ethyl bromine, and so this means it's protic. Or sorry, not protic, aprotic. And this is, of course, also protic, and it is a 2 prime. which means it's going to be SN2. It's just a matter of figuring out where we're going to add. And of course, what we're adding is this molecule, ethyl bromine. It's actually like this. And so, of course, this is going to be a leaving group. It's going to leave, and you're going to be left with just this little carbon thing. And you have a little one here somewhere. And to figure out where it's going to go on this molecule. And in fact, for that, we need to look at the conditions. And so if you look, we have LDA at a cold temperature. So because we have LDA at a cold temperature, this immediately indicates that this is going to favor the kinetic product, which means it's going to form at the less stable alpha carbon atom. And in this case, it's this one on the end. If this were like butoxide or ethoxide, any methyl like oxide really, at a kind of high temperature or room temperature, like 20 degrees Celsius, then this would favor the more substituted carbon, which would be this one. But we don't have that. We only have LDA at low temperature, so it's going to bond to this end right here. And so when we add this onto there, you're going to end up with that, and that produces that answer, right? And that's that for that. And lastly, we look at I. This one is like a little deceptive because you think it's going to be hard. It looks a little bit weird because you have acid and water. But really the mechanism for this is the same as this. It's literally the exact same. Because sulfuric acid has the same kind of properties as like the direction that HX would go under is the same as that of H2SO4 and just H2SO4, no other acid, I don't know why, just that's how it is. And what's going to happen is that you're going to have the molecule right here. You're going to break this alkene, and one of these hydrogens, when this alkene is lost, like this, more or less. Whoops. It's going to take one of these right here, and then when you have this oxygen, which is negative charge, then it's going to bond to the more substituted carbon, and that's going to give you this product. Hope that helps.